Today's topic is chirality. Chirality, that is a funny word. At least it is to me the first time I heard it. And in order to demonstrate something about chirality before we actually learn the specifics of what it is, let's start with a little exercise that you can all do sitting in your seats right now. I want you to hold up your two hands. Now I want you to look at them and tell me what you notice. We'll just start there. What do you notice?
Skin.
And they're covered in skin, hopefully. What else?
They're even. They're symmetrical. Correct.
So they have some kind of symmetry going on here. So you're saying just in general, minus any small imperfections or changes, your left hand is much akin to your right hand, and vice versa. Right?
You don't mean the lines, you just mean like the fingers themselves.
I said minus any small details like lines or even your fingerprints themselves. Little side fact, if you look at your fingerprints, the one on your left index finger is not the same as the one on your right index finger. And there's actually different patterns of fingerprints that you can have. You might have a swirl to the left clockwise or something, or counterclockwise, or you might not have a swirl. Anyway, that's a topic for biology or another class like that. But the important thing is, as Tommy pointed out, that they are much the same. What's that? Much the same, right. What else, though? What can we talk about with this symmetry?
Are you still talking about hands?
Hands, yeah.
Well, they go together well, I guess.
They go together?
Yeah. I think that you were going somewhere.
Let's head in that direction.
Oh.
Tommy, I saw you doing something over there. What were you?
They're the same length?
Okay, you were overlaying them on top of one on top of the other, right? Now, even so, we can do this. Is the configuration or the conformation the same?
You mean like 5 fingers on each hand?
That's something more subtle. Like, let's say, in order to do this, I have to have the palm side of one hand facing to that side of the room, and I have to have the palm side of this hand facing to the other. If I try to overlay them with the palms in the same direction, what happens? Just give it a try.
It doesn't match up?
It doesn't match up, right?
Oh,
You do at least.
It doesn't match up. This is what, in the short, chirality is all about. What it is that in chemistry, sometimes we have molecules that look the same. They seem to be mirror images of each other, but just like you and your mirror image when you look into a mirror, there's no way that you could ever line them up so that, or rotate them or something of that fashion, so that they would be exactly the same. Like, there's no way that I could turn any one of my hands so that the thumb problem here goes away, so that the thumbs would always
Cut off your thumbs.
be in the same direction there. There's no rotation that I could do, that I could perform with my hands to get them to line up the same. Nothing. So let's write some things down about chirality. So we started here doing our hand example. I guess I should note that this is chirality up top. So what we just did, and I'm going to draw a hand here. It'll be a quick hand. Probably won't look much like a human hand, but use your imaginations. Thumb here. right hand.
Ooh.
We're gonna fix this one a little bit. There we go. Left and right hand. These hands may have been in some sort of accident or something, but you get the idea. Let's fix this pinky here. Maybe a little bit better. Just fix a little too wide there.
That one looks good.
This one, they broke their wrist,
Yeah.
as you can clearly see here. And it's funny because I've broken my right wrist, so maybe this is a subconscious thing. So our left and right hands. They cannot be superimposed. You can't take your right hand and put it on your left hand in any way so that they'll exactly line up. It won't work. So we'll put point 1, point 1. No rotation will produce an composable image. This, referring to what came above it here, the no rotation, is called chirality. Would anyone like to take a guess as to why in chemistry, when we come across molecules that cannot be superimposed, they might look exactly like mirror images of each other, so they're made of the same things, but we have a left-hand version and a right-hand version. Why would that matter? Why don't you just take some guesses here? Being wrong is the best way to sometimes figure out what's right.
Something like spin.
What's that?
They like spin or something. Like
Are you talking about
one side's like not.
Go ahead.
Like one's positive and one's negative, so it can't. Like if you line it up in like a different way, it forms a totally different bond.
I like the way that you were thinking with that, yeah. And I think you're kind of hitting the main point, actually. And that's that we come across molecules. And I'm going to use our body as an example because it's a great source of chemistry in and of itself, and it's one that we're most familiar with. We have these left and right-hand version of molecules that we have inside of us, and sometimes that we might ingest or encounter in some fashion. And often, there's only one side, either the left or the right, that we actually use inside of us to do chemical reactions and things. And it's often the case that the other version of it, even though it's the same thing, it just is that mirror image, can be very, very harmful to us. So it's not just like there's a slight difference. It's that one, it helps us and is good for us. The other, made of the same thing, very harmful to us. So that's pretty interesting, if you ask me, because usually we think, well, maybe a different substance would be harmful to us. But no, in this case we're talking about same thing, same chemical formula, just a mirrored image of the other. And all of a sudden it has totally different chemical properties. And that's why in organic chemistry, we take time to talk about these because we are often worried about the chemical properties of organics, how they react and what they're capable of doing. We'll get into the specifics of that in due course, but for right now we're going to start learning about what else constitutes chirality and look at some examples. So, point 2 here. Let's look at chiral molecules. So I think we already have a maybe, hoping, rough idea in our head about what a mirror image of a molecule might be. And that's a good place to start. So we're going to begin with a simple example, but it's actually one that's very indicative of things that you'll look for when identifying chiral centers and chiral molecules in general. We'll worry about chiral centers in a second. A simple example is carbon bonded to 4 different groups. Carbon bonded to 4 different groups. The first thing that we're going to do is identify that carbon is a chiral center. So we know we have carbon in 4 other different groups bonded to there, and what we need to do is, for the sake of this example at least, is pick one of those atoms that will serve as the point that we try to rotate everything around to see if we have an instance of chirality in there. So, let's see the example that I wrote down here. Let's do this. Let's say we have a central carbon here, bonded to a methyl group up top. Let's say over here we have bromine. Maybe going into the board we have a hydrogen. And coming out of the board, let's do an alcohol, a hydroxyl group. To draw its mirror image, CH3 up there, bromine here, hydrogen going into the board, alcohol back there. Alright. Now we just said that carbon is going to be our chiral center, so this is what we're going to try to rotate everything else around to see if we could match this, we'll call this the left version right now since it's on the left side of this image, with the right version over here. What do we think? Is there any way that we could flip this around and make the left one exactly like the right one?
Couldn't you just switch where the bromine and the hydrogen and oxygen are?
Okay, so...
Or, well, the hydrogen and oxygen are in different orders, so...
You mean here?
Yeah, here and on the other side, so...
Well, just, this is bonded to the oxygen, the hydrogen is bonded to the oxygen here, so that's okay. Well, let's say we try to just rotate it that way. So we trying to rotate it, everything shifted here to the right in the plane of the board. So in this case, we would have our OH that would slide over 1. So it would now be coming out of the board there. And our bromine would slide over one there, and our hydrogen would move over one there. If we try to rotate it again then, what we would find, it's kind of hard to visualize though on the board, but maybe if you want to use your hands, if you take, since we're just dealing with bottom atoms here, and maybe take 3 fingers, whichever ones you want, and say like your hydrogen is in the back, so that would be your thumb. Your bromine would be the one that's kind of in the middle, and your OH would be the one that's coming out. Try to rotate it there, and what you'll find is that even if you get your OH group to the other side in this molecule, it's not going to be coming out like it is on this one. This is an example that matches exactly like with your hands. Whatever you consider here to be the thumb, you're never going to get it to line up with the other one. So we'll say,
Is that kind of like saying, like maybe your OH there is like your thumb, and then VR is like your pinky? And it's like trying to put your pinky where your thumb is. It's like,
yeah,
like you can't.
you can't do it. And you're exactly right. So again, no rotation. Will match these two perfectly. There's nothing we can do. We can't rotate it in any fashion. We have another name, rather than saying that carbon is the chiral center. We can say, in general, and of course when we say general, we're taking this case as we have it here, and we're pushing it into a whole bunch of different realms of chemistry in this sense, so we might not necessarily have to be a chiral scenario. But we have a name for these center atoms that produce these kind of isomers, stereoisomers of each other. Let's say in general, carbon is a stereo center. Stereo center. Anyone ever configured with sound settings or something, and you see that there's a stereo option? What does that mean?
2 different audio sources. It's like some will play one side and some will play the other thing.
Right, yeah, so we have like a left source and a right source. So maybe you can kind of see why that word usage here in center, because we know we're talking about the center atom, and stereo, because we have a left and a right version of it. So, stereo, think of your stereos in your car or anywhere that you have sound like from a TV at home. Usually there's a stereo configuration where if you have 2 speakers coming out the left and the right, so you have 2 sources, just like in this case, we have 2 versions of essentially what looks to be the same molecule. Let's do some examples, some identifying examples, because this is what your assignment is like. Our first example is going to be chlorocyclopentane. Chlorocyclopentane. And I know we haven't talked too much about naming in here. And part of the reason I don't focus on that with you right away is that it helps if you, in my opinion, if you actually work with them and try to use them in different ways. It gives different connections in your brain to the name itself. So if you're thinking of what's a cyclomolecule, this you should remember from when we talked about ring structures. Pentane, you might know the pent right there, how many carbons we're dealing with. Ane, type of bonds. And chloro, you might be able to identify that with an atom or an element on the periodic table. But it helps if you have a sense to tie these names to. If you don't, I think it just becomes a matter of trying to memorize a lot of information that's disparate and that you can't maybe recollect as easy as you'd like. So what would you wager that chlorocyclopentane looks like? So we have a ring structure, right?
5.
Right, so the pen part there is 5. Cyclo means it's a ring, so. Alright, now, what about the chloro part there? Chlorine, right. So, what do you think I should do with chlorine?
Attach it somewhere?
Brilliant. Now I'm going to put my hydrogen here. This carbon has 2 bonds and there's 2 more hydrogens. Same with this one. And this one. Same with this one. This one has 3, so it just needs 1 more hydrogen. Before we draw anything with a mirror image, so I think it's good to visualize on your own a little bit. Do we have any stereocenters or chiral centers here? That's always your first task. So look and see, is there, in this case a carbon obviously, is there a carbon that has 4 different groups bonded to it? Or 4 different things bonded to it? Yeah, well, let's look at it.
There's 3 bonds. So with chlorine up with double bond?
We have 1 here with chlorine, 1 here with hydrogen.
Oh, wait. More than
1, 2, 3, 4. 1 here to CH2, another 1 here to a CH2. So, this isn't bonded to 4 different things. Because it's 2 of the bonds are to a CH2.
Yeah.
So in this case, this carbon is not a chiral center. And I think quickly you could figure out, looking through that you don't have any chiral centers here. So if you did actually, now we'll take the mirror here. You could rotate the left one here to be exactly like our right one. All you have to do is not quite 180 degrees, I guess, but if you just turned it that way, you would have your CH with the chlorine there on the other side. The only thing is that this chlorine would be angled down, but that doesn't mean anything. It's just the way that we're writing it. It's still the same thing. So, cyclopentane, not a chiral molecule. not a chiral molecule because we don't have any chiral centers. So of course it can't be a chiral molecule. We can make its mirror image look just like it. Let's try another one here. What was that? 3.1 over there, so 3.2 has to go here. So now let's deal with bromochlorofluoromethane. There we go. Bromochlorofluoro. That'll look better. Fluoromethane. And maybe now you're starting to see that names in organic chemistry can get quite long. But they are exactly telling you what's in there, which is the beauty of it. Most people have this idea in science that there are names for things that don't make sense, or they're like, why can't we just call them something simpler? When in fact, you're calling them exactly what they are, and you couldn't get any simpler. And in fact, if you try to simplify it, the way that you simplify it often becomes longer than the name itself. So, what do we think this looks like?
Got some bromine in it.
Okay, so we have bromine, exactly, you're right. Let's start here in the end, actually. We have methane. I think that's probably the easiest.
Non-carbon.